Hello everyone, welcome to my class. In today's class, I am going to cover the cross product of vectors. Let me start the class right away. Quick recall, there are two types of vector multiplications, the dot product and the cross product. In our last class, we covered the dot product of vectors, and today I am going to cover the cross product of vectors. Next, let me give you the definition of the cross product of vectors. For two vectors in the space, u vector and v vector, where u has component a, b, c, and vector v has component p, q, r, then their cross product is denoted by u cross v and is defined as u cross v equals to this 3 by 3 determinant. First row I, j, k, second row the vector u component, and third row vector v component. Quick visualizations. For the cross product, our input are vectors u and vector v, and after we take the cross product, the output is a vector which is u cross v. First, let me recall how we expand the determinant. The determinant of a 2 by 2 matrix is a, b, c, d, and we expand, we multiply this diagonally, a times d, and we subtract by multiplying this diagonally, so minus cb. So then this turns out to be ad minus bc. Similarly, the determinant of a 3 by 3 matrix is given by, let's say our determinant is a1, a2, a3, b1, b2, b3, c1, c2, c3. Then we are expanding along the first rows. So first term is plus, second term is minus, third term is plus. So write a1, then cancel all the elements along the rows and columns containing a1. So that means this cross out, this cross out. What left? I have a b2, b3, c2, c3 right down here. And the next term minus a2. Again, cross out the rows and columns containing a2. Then write down the determinant here, which is b1, b3, c1, c3, which is here. Similarly, plus a3, cross out the rows and columns containing a3. So we have b1, b2, c1, c2 left. That means we reduce this 3 by 3 determinant into 2 by 2 determinant. Then you can use this first idea to expand the 2 by 2 determinant. Awesome. So that means with this idea, we can expand our u cross v, this determinant. Great. So let's move on. Geometrically, consider a plane determined by two vectors u and v, placing their tails together with making an angle theta. So now I am giving you the geometric definition of cross product. So u vectors, v vectors, place both of the tails together making an angle theta. Then the cross product is, which is u cross v, is orthogonal to both u vector and v vector. That is, u cross v is orthogonal to u cross v is orthogonal to v. Quick fact, the magnitude of u cross v turns out to be magnitude of u, magnitude of v times sine theta, where theta is angle between u and v. And interestingly, this magnitude means the length of this vector turns out to be the area of the parallelogram determined by vector u and v. So this u vectors, this v vectors, and construct a parallelogram here. So this v vectors here and u vectors here. So this construct a parallelogram. Then this length of this u cross v turns out to be the area of this parallelogram determined by u and v. So that is the area of parallelogram equals to the magnitude of u cross v equals to magnitude of u magnitude of v times sine theta. So the picture is here. So the area of this parallelogram turns out to be the magnitude of this u cross v vector. Great. And on the other hand, the area of the triangle is then means the area of this triangle here. If I join this diagonal here, or if I join this diagonal here, then this gives us two triangles. So the area of a triangle is half of the area of this parallelogram. Awesome. Next, let's talk about properties of the cross product. Cross product is anti-commutative. So if we switch the position of vector, then we have a minus sign there. Cross product is distributive over the vector sum. Properties C. So property C, K is a scalar. K times u cross v equals to K u cross v or u cross kv. So we are only multiplying one of the vectors by this scalar. Property D, this AU cross BV, where A and B are scalar, equals to, we can pull the constant or scalar outside and take the cross product of the vectors, or we can multiply U by both scalar and then cross with V, or we can multiply the V vector by both of the scalar AB and then take the cross product with U. A triple product is U dot V cross W equals to U cross V dot W. That means we can switch the order of dot and cross here. And triple product, which is a vector, that means vector triple product, which is U cross V cross W equals to U dot W V minus U dot V W. We only focus up to E. Another quick remark, U vector is orthogonal to W vectors and V vector is orthogonal to W vectors, implies, that means if and only if W vector is parallel to U cross V. Great. Let's move on. Some consequences from the definition of cross product in geometric form. So we know U cross V equals to magnitude of U, magnitude of V, sine theta, and the normal vectors n. Then U cross V equals to 0 if and only if U is parallel to V, because for the parallelism we have either theta 0 degree or pi. In both conditions our sine 0 is 0, sine pi is 0. So U cross V is 0. If I cross the vector itself, always happen to be 0 because the angle is 0 degree. Third, the cross product of the coordinate unit vector, that's our standard unit vector I, j, k. If I cross to itself, it gives us a 0. I cross I is 0, j cross j is 0, k cross k is 0. And if I cross I and j, it gives me k. So in this diagram here, I cross j is k. So I'm going counterclockwise here. J cross k is I, k cross I is j. If I go other direction, then it produces the minus. For example, I cross k is minus j, k cross j is minus I, j cross I is minus k. Awesome. I hope this makes sense to you all. Let's move on. Another note, the cross product is not associative. For example, I cross j. So inside the parenthesis I cross j is k. So then I cross k is minus j. But if I switch the ordering here, first take the cross product between I cross I, that produces 0, and 0 cross j is 0 vector. So minus j is not 0 vectors. That means the cross product is not associative. Great. Next, there is a small comparison between dot product of vectors and cross product of vectors. the dot product, the first column, the second column is cross product. In the dot product, it gives the angle between two vectors using cosine theta. So cosine theta equals to u dot v over magnitude of u, magnitude of v. And to the second column, the angle between two vectors is given by the sine theta, magnitude of u cross v over magnitude of u, magnitude of v. Similarly, under the dot product column, the dot product u cross v is maximum if and only if u vector is parallel to v vector. And then under the cross product column, the magnitude of u cross v is maximum if and only if the vector u is orthogonal to v vector. Lastly, under the dot product column, the dot product is 0 if and only if vectors are orthogonal. Under the cross product column, the cross product is 0 if and only if the vectors are parallel. Great. I hope this small comparison makes sense to you all. Now let's move on. Next, let's talk about the scalar triple product, which is denoted by u dot v cross w. So consider the parallelepiped. I call this is PP, short form, determined by three vectors as shown. So here, let's talk on this diagram here. This is the u vector, this is the w vector, and this is the v vector. Cross these two vectors v and w. This v cross w is this orthogonal vector to both w and v, and the magnitude of this cross product, means the magnitude of this cross product, turns out to be the area of this base here, of this parallelogram here, the base. And we have another vector u. Now we are talking about finding the volume of this parallelepiped. So first we know the area, which is the magnitude of v cross w. Now let's find the height. The height is given by this here, which is nothing, simply the scalar projection of u onto v cross w, which happens to be simply the magnitude of u cosine theta. Theta is angle between u and v cross w. So then the volume formula is v equals to A means area, h means height, right? Great. So area of the base is the magnitude of v cross w, and the height is h, which is magnitude u, magnitude cosine theta. So now we have this expression here. Then from here to here, this is simply the dot product between two vectors v cross w dot u, its magnitude. Hence, volume of the parallelepiped determined by three vectors u, v, w is simply u dot v cross w. This is simply the scalar triple product. Quick recall, the scalar triple product is just the 3 by 3 determinant. This is the u vectors component, the second row is v vector component, third row is w vector component. So the volume equals to scalar triple product. Scalar triple product equals to simply 3 by 3 determinant, and we know how to expand this determinant earlier. I hope this makes sense to you all. Now let's move on. Quick note, three vectors, vector u, vector v, and vector w, or 4 points, lie on the same plane if the scalar triple product is 0, which is called coplanarity. Or we know the three vectors determines the parallelepiped. If the parallelepiped, the volume is 0, that means the parallelepiped is smashed on the ground, so then we don't have any parallelepiped, so the volume will be 0, means all of these three vectors are coplanar. Great. So let's move on. Next, application of cross product. We define the torque using cross product. Suppose force F is acting on the range range lies on the x-axis. Here, the bolt is here. At a point whose position vector is r, then the torque twisting force is denoted and defined by, we denote by tau. Tau equals to r cross f. Means we are forcing the wrench, means we are tightening the bolt. Then we are finding that twisting force. The formula is simply tau equals to r cross f. We are holding the wrench here, so we find the position vector, and we are putting the force in this directions, which is a force vector. Then torque equals to r cross f, which is by definitions magnitude of r, magnitude of f, sine theta. Awesome. Now with this theory concept, now let's do some example. First, worked examples. Suppose we have three vectors in the space or in R cubed. U vectors with this component, V vectors with this component, W vector with this component. Then compute the following bunch of sub questions, part A through part Z. So first part, find the cross product U cross V. So we by definitions we define the cross product using the 3/3 determinant. So the solution is, first put I, J, K in the first rows, second row put the component of U vectors, and then the third rows put the component of V vectors. Then let's expand this determinant. We know how to expand this determinant earlier, but let me show you here. So first write down the I, then cross out the columns and rows involving I, so that I have 1, -4, 2, 1. That's a 2/2 determinant, and multiply this diagonally. So this is 1 times 1, and put minus from formula, 2 times -4. That means 1 minus -8 is +8, so 9. 1 plus 8 is 9, so 9i. And then the second is a plus minus plus, so the minus, so put minus j, then hide this column, hide this row. Then we have the determinant of 8 minus 4, 5 and 1, and multiply this diagonally. 8 times 1 is 8, and then going this way is minus, so minus 5 times -4 is plus 20, so 20 plus 8 is 28, so then 28 here. Similarly, plus k, then hide this column, hide these rows involving k. Then we have the 2/2 determinant, 8, 1, 5, 2. Multiply this diagonally, multiply this diagonally. When you multiply this diagonally, we need to put minus sign. So 8 times 2 is 16, minus 5, so plus 11k. I hope this computation makes sense to you all. Now let's move on. In part B, compute V cross U. I told earlier the cross product is anti-commutative, so that means V cross U gives us a minus U cross V. So let's verify here. So again 3/3 determinant with this one, that's better. And first row I, J, K, second row component of V vector, then third rows component of U vectors. Then let's expand this 3/3 determinant. Again we are expanding along the first row, so plus, minus, plus. First plus, so I as it is, cross out this row containing I, the column containing I, so we have 2/2 determinant, which is 2, 1, 1, minus 4. Then let's multiply this diagonally. 2 times -4 is -8. Then from formula minus, 1 times 1 is 1. So minus 8 minus 1 is -9 I. Next, minus j, so put minus j, then cross out this second column and then the first row. Then we have the 2 by 2 determinant 5, 1, 8, negative 4. Then multiply this diagonally, so 5 times minus 4 is minus 20, minus 8 times 1 is minus 8, so minus 20 minus 8 minus 28, and from that minus 1 formula plus 28. Similarly, plus k, then cross out the last column and the first rows. Then we have the 2 by 2 determinant 5, 2, 8, 1. Multiply this diagonally, and subtract this diagonal multiplications, right? So 5 times 1 is 5, minus 8 times 2 is minus 16. So 5 minus 16 is minus 11. So if you compare part A and part B solutions, the part A equals to, the solution of the part A equals to minus here in the solution of part B. Great. So now we verified this, the cross product is anti-commutative. Great. Let's move on. Part C. Let's compute this U dot U cross V. So, I mentioned earlier the cross product U cross V is orthogonal to U and orthogonal to V. So that means I'm going to get 0 here. So I'm taking the dot product of U and U cross V. So here U cross V we already found in part A. So U cross V is here, is 9i minus 28j plus 11k, and U vector is given to us 8i plus j minus 4k. And let's take the dot product. The idea is we multiply the corresponding component and add them. So we multiply 8 times 9, multiply 1 times minus 28, multiply minus 4 times 11, and add them, which is 0. So this verifies the U cross V is orthogonal to U. Similarly, U cross V is orthogonal to V. So to show this part, all you need to show the dot product of U cross V with V equals to 0. Awesome. Let's continue. Let's compute the scalar triple product. We know the scalar triple product is U dot V cross W or U cross V dot W. We can switch the dot and cross here in the scalar triple product. Let me use the result we found earlier. So U cross V is again we found in part A, which is 9i minus 28j plus 11k. We found here, and W vector, and the W vector is here 2i plus 3k. So no j here. That means we can put 2i plus 0j plus 3k here. So 2i plus 0j plus 3k. Then take the dot product, multiply the corresponding component and add them. So I'm multiplying 9 times 2, 18, minus 28 times 0, 0, plus 11 times 3 is 33. And then 18 plus 33 is 51. Another way to compute the scalar triple product using this 3 by 3 determinant. So we can use this determinant. So first rows U vectors component, second rows V vector component, third rows W vectors component. So then here this is U vector, this is V vector, this is W vectors, and we know how to expand this 3 by 3 determinant. Again, let me go over here. First, let's expand this 3 by 3 determinant along the first rows. So here is a plus, here is a minus, here is a plus. So first plus 8, then cross out the first rows and first column containing 8. So we have 2, 1, 0, 3 determinant left. So let's expand this one. 2 times 3 multiplies 6, minus 0 times 1 is 0, so 6. So we have these terms. Next, minus 1, cross out the second column and the first row, then we have the determinant of 5, 1, 2, 3, then multiply 5 times 3, 15, minus 2 times 1 is 2, so 15 minus 2 is 13, which is there. I hope it makes sense to you all. And then lastly the minus 4, then cross out the third column, then first rows containing minus 4, then we have the determinant of 5, 2, 2, 0, then multiply 5 times 0, multiply 2 times 2, and when you are multiplying this 2 times 2, we need to subtract this product from this diagonal product. That means 5 times 0 is 0, minus 2 times 2, 4, so then minus 4 is here. So simplify, it gives us 51. So we have two ways to find the scalar triple product, one using this 3 by 3 determinant, one using this cross and dot product idea. We have the same answer. Let's move on. Part F, the volume of the parallelepiped determined by three vectors u, v, w is by definition just the scalar triple product, which we already computed here. Answer is 51. That means we found the volume of parallelepiped using this scalar triple product. Question G, are these vector u, v and w coplanar? If these vectors are coplanar, then their scalar triple product will be 0, or the volume of the parallelepiped determined by these three vectors will be 0, but part F is not 0, so these three vectors then are not coplanar. I hope this makes sense to you all. Great. Now let's move on. Example 2. Suppose 3 points P, Q, R are given in the space. Answer the questions part A and B. Part A, find a vector orthogonal to the plane through 3 points. We know 3 points determines a plane. So the questions A ask us find a vector orthogonal to the plane through 3 points. So how to find a vector orthogonal? We have to take a cross product. Now to take a cross product, we do need 2 vectors. So let's find the 2 vectors. So, and we know any 2 points gives us a vector by using the formula tip minus the tail. So first, let's assume our vector u, which is pq. That means q minus p. So q minus p, that means minus 2, minus 1, minus 3, 1, minus 0, 1, 3, minus 1, 2. I hope this computation makes sense to you. And another vector is v vector, which is pr. That means r minus p. That means 4 minus 1, 3, 2 minus 0, 2, 5 minus 1, 4. So now we have 2 vectors pq and pr both lying on the plane. Now if we cross them, that gives us a vector normal to these both of these vectors. That means normal to the plane through these 3 points. So now let's cross them. So then u cross v. Again, we compute the cross product by using this 3 by 3 determinant. The first row with I, j, k, second row vector u component, third row vector v component, and use this 3 by 3 determinant to find the u cross v. So let's do again here. So now let's expand along the first row. So then plus, minus, plus. So then write down the I. Oh, there is no I. Maybe we may get 0 here. Let's see. So then I, then what left? Cross out the first row, first column. We have left 1, 2, 2, 4 determinant. Then let's multiply this diagonally. 1 times 4 is 4. Minus 2 times 2 is 4. So 4, 4 cancel out. So no more I terms here. The next term is minus j. So minus j. Then cross out the second column, cross out the first row. We have the 2 by 2 determinants, negative 3, 3, 2, 4. Then let's multiply this diagonally. So minus 3 times 4 is minus 12. And then multiply this diagonally, minus 3 from formula, minus 3 times 2 is minus 6. So minus 12 minus 6 is minus 18, and the earlier minus sign from formula makes this positive 18j. Similarly, the third term is here. So let's write the k, then cross out the third column and first row containing k vector. Then we have the 2 by 2 determinant of negative 3, 1, 3, 2. Then multiply this diagonally, multiply this diagonally. So then minus 3 times 2 is minus 6. Then minus from formula, minus 3 times 1 is minus 3. So then minus 9. So we have minus 9 here. So either you write in this form using ijk, or in this form using angular bracket. So 0 means no I component. So 0, comma 18, comma minus 9. Great. This vector, or just take this factor 9 out, then we have 0, 2, minus 1, or this vector, or any non-zero scalar multiple thereof is a required orthogonal vector to the plane containing these 3 points. I hope this computation makes sense to you all here. Let's move on. Part B. Find the area of the triangle PQR. We know the area of the triangle is the half of the area of the parallelogram determined by these vectors. But here we are using this idea. We first find the U cross V, and then we take the magnitude. The magnitude U cross V is the area of the parallelogram, and we divide by 2. And that's the formula. Let me show you the formula here quickly. That's the formula here. Okay, so here. Okay. So that's the formula here. So find the cross product, which is a normal vector. Take its magnitude. Its magnitude happens to be the area of this parallelogram determined by these two vectors, and divide by 2 for the area of the triangle. The area of triangle is half of the area of this parallelogram. Awesome. So let's move on. Let me scroll down. We are talking in example 2, part B. So then by formula, area of the triangle PQR equals to 1/2 magnitude of U cross V, 1/2. We already found U cross V here, which is this vector. Let's find out its magnitude. So then under the radical, 0 is square plus 18 is square plus minus 9 is square. It turns out to be, after simplifying, it gives us 9/2 radical 5. That's the square unit. That's the area of the triangle determined by PQR. Great. Now let's move on. Let's do example 3, the applications of cross product of vectors. Suppose a bolt is tightened by applying a force 50 Newton to a 9-meter long wrench. Find the magnitude of the torque vector about the center of the bolt if the angle between the force and the wrench is pi-third. So let's apply the formula. So solutions by formula. The magnitude of tau, or the torque, equals to magnitude of R cross F. We know R cross F is magnitude of R, magnitude of F, sine pi-third. And the theta is pi-third here. We know magnitude of R is 9, magnitude of F is 50. We know sine pi-third is radical 3/2. Then after simplifying, this gives us about 389.7 joule. Awesome. So we finished the cross product of vectors today. So in the next class, we'll talk about equation of lines and planes. Thank you.